Howdy, this is Mr. Potter. Today we're going to be talking about differentiability. We've been talking about derivatives for the past couple of days, what a derivative is, what the practical purposes of a derivative are. But today we're going to talk more about the general sense of differentiability. So the question is, of course, what is differentiability? Basically, a function is differentiable if it has a derivative. And so I can talk about being differentiable at a point if it has a derivative at a point. I can talk about it being differentiable on an interval if it has a derivative on an interval. I can talk about it being differentiable on its domain if it has a derivative for every value in its domain. And so we talk about the derivative and we talk about differentiability interchangeably. When basically what we're saying is that if a function is differentiable, then it has a derivative to work with. And so what we need to talk about is when does a derivative not exist? And we're going to take a look at this from two different viewpoints. The first one is, remember that the derivative at a particular value is the limit as h approaches 0 of my function at x plus h minus f of x over h. And we also talked about how I could talk about the derivative at a particular point being the limit as x approaches a of f of x minus f of a over x minus a. Key thing to remember here is that in either of these cases, the derivative is a limit. And so if I want to know when the derivative does not exist, I basically have the situation where f prime does not exist. When the limit does not exist. And we've talked about the limit when it exists and when it doesn't exist quite a bit throughout chapter 2. There's basically a three-step process that we're looking at. Remember, the first step is that the limit as x approaches a from the left of f of x minus f of a over x minus a. This has to exist. And the limit as x approaches a from the right side of f of x minus f of a over x minus a. This has to exist. And they have to be equal. So it's going to look like this. Basically, I'm either going to be missing my left limit, I'm going to be missing my right limit, or most likely, for the problems that we'll be facing, is that those left and right hand limits won't be the same. Of course, in the case of our original definition of the derivative, I'm looking for the limit as h approaches 0 from the left, or the limit as h approaches 0 from the right. So these are the limits that we've talked about here, and of course step 3 is that they have to be equal. So from a limit standpoint, the derivative does not exist if the limit does not exist. In other words, it fails one of the 3-step process that we followed to determine when a limit exists. So a better question would be, when does a limit does not exist from a graphical standpoint? So for a graphical standpoint, a limit is going to have a problem whenever the slopes from the left and right are not equal. Remember that the primary graphical practical use of the derivative was to deal with the slopes of the tangent line. So the situation where I have a slope coming down one way and then changing direction so that the slope of the tangent lines are not a smooth transition. The slopes as I approach a particular point from the left are not equal to the slopes as I approach a particular point from a right. Any of those situations are going to be a place where my derivative does not exist. And so anytime I have a corner on my graph and y equals the absolute value of x is a beautiful example of when that situation happens. For every value less than 0, the slope of my tangent line is -1. And for every value larger than 0, my slope of the tangent line has a value of +1. And so at 0, those slopes aren't the same. And so you can see from a limit standpoint, the limit of my slopes of tangent lines from the left were -1. The limits from the right are +1, and the left-hand limit doesn't equal the right-hand limit. The slopes from the left and the slopes from the right aren't equal. So if I have a corner, or if I have a cusp, a situation kind of like y equals the cubed root of x squared. So this is an even function that has a lot of similarities with the absolute value function, but it's not a actual corner. What I've actually got is a curved tip here. So we call that a cusp. And the third situation is whenever I'm dealing with vertical tangents. Because if I'm dealing with a vertical tangent, say like the cubed root of x, this odd function has a situation where I've got this transition here and then here. And the thing is, as I approach 0 from the left, my slopes are actually approaching positive infinity. And the same thing's happening over here. So even though the limit of these slopes is approaching positive infinity, positive infinity is not a well-defined number. And if we had a situation where the limit of a function as x approaches a equals infinity, then we would say that that limit does not exist. And if the limit does not exist, then the derivative does not exist. So the three situations we deal with where a derivative does not exist from a graphical standpoint are when my graph has a corner or a cusp or a vertical tangent. And there's actually a word that mathematicians use for these situations. We talk about a function being smooth. If there are none of these corners or cusps or vertical tangent, and smooth is synonymous with being differentiable. We would say that a function is smooth if it doesn't have any of these corners or cusps or vertical tangents. We say a function is smooth if the derivative exists for all points on its domain. We could say a function is smooth on an interval if it's differentiable on an interval. So then the next question is, what does differentiability mean? I mean, aside from the idea that f prime f a exists, what does it mean for a function to be differentiable? And it means a couple of things. One thing that it means is this idea of locally linear. In other words, if I were to take a graph that has some type of curve to it, and I know that there's a tangent line at a particular point, but if I were to zoom in to this region, I'm going to see that this tangent line almost approaches the idea of this curve. And if I continue to zoom in, eventually I'm not going to see much of a difference between the curve and the tangent line. They'll seem to almost superimpose. So in other words, we call it locally linear if, for sufficient zooming in, my function really doesn't differ from the graph of the tangent line. So my graph, as I zoom in closer and closer, looks like a straight line. So from a graphical standpoint, that's what differentiability means to us. It means locally my graph is linear. Locally, for some domain around the point that I'm looking at to get the tangent line, somewhere around there, the tangent line is actually a very, very good approximation. I'm going to be off by just a little bit if I use that tangent line to approximate. And we'll talk later on in this book about how to use the tangent line to approximate the value of a function. So one way of looking at this is the idea of being locally linear. In other words, the tangent line is a very good approximation. It's a very good representation of my graph for some small intervals surrounding the point of differentiability. But the other thing that we have for what does differentiability mean is that if a derivative exists, differentiability implies continuity. In other words, if I know that the derivative exists at a particular point A, then I know that f is continuous at that point. And if the derivative exists on some domain, then I know that f is continuous on that same domain. So the fact that a function is differentiable actually tells me a little something about whether or not my function is continuous. It tells me that it is. So knowing that a derivative exists gives me continuity for free. Knowing that a derivative exists means I don't have to go through that three-step process of showing that the limit exists, the function is defined, and those three values are equal. So there are two ideas that we get out of this relationship between continuity and differentiability. The fact that differentiability implies continuity. And by the way, the converse is not true. Any of those examples that I gave you a few pages ago, where I have a corner or a cusp or a vertical tangent line, all of these functions are continuous, but none of these functions are differentiable at the particular troublesome point. So differentiability implies continuity, but continuity does not imply differentiability. So the last thing I want to talk about is the concept of the intermediate value theorem. The idea here is that if I know something about the behavior of the function, then I can make predictions about what happens between two particular points. So the first one I want to talk about is the intermediate value theorem for functions. And so what we're doing is we're saying that if f is continuous on some domain, then f attains every value between f of a and f of b. In other words, if I know that my function is continuous, but everywhere between a and b, then I know that no matter where f of a is, and no matter where f of b is, I know that every value between f of a and f of b gets hit at least once by my function, even if I go outside the bounds of this. The thing is, no matter what value I choose, there's got to be some point in between a and b where my function hits that value at that point. So this idea of the intermediate value theorem means that if I know that f of 2 equals 7 and f of 3 equals 11, and I know that f is continuous on this domain, then I know that there's some f at c that's equal to 8. I know that I can find c, and I know that c has to be on this interval from 2 to 3. And I can do this for any value that lies between 7 and 11. So this is what continuity brings to the table. It brings this idea that there are no holes, there are no gaps, there is no place that my function could kind of sneak around, so I never get a y value that lies between two given y values if my function's continuous from those y values. And I can say the exact same thing about derivatives. The idea here is that if f is differentiable on an interval, on some interval a, b, then there has to be a c in that interval, a, b, where f prime of c lies between f prime of a and f prime of b. In other words, if I have a function that is smooth, a function that doesn't have any vertical tangents, doesn't have any corners or cusps, and I've got a situation where the tangent line here has a slope of 0 and the tangent line here has a slope of 2. That means there's got to be some place where if I wanted to find where the slope is 1, there's got to be a place somewhere where the slope is 1. There's got to be some place between a and b where the derivative is 1. There's got to be some place in here where the derivative is 0.5 or 1.5 or any value between 0 and 2. There's got to be a place where the derivative has a value. There's got to be some x coordinate where the derivative at that x coordinate has to lie between the given derivatives. And so this allows us to have another practical use of intermediate values. Let's say, for example, that I'm traveling on a highway and I start off at 45 miles per hour and I end at 60 miles per hour. Now, the thing is, my car isn't going to do any sudden jumps in velocity. As I'm driving, my acceleration tends to be a very smooth function, and therefore my velocity is very, very smooth. And so I can know that at some point on my journey, there was a place where I hit 53 miles per hour. Somewhere between where I started at 45 and where I ended at 60. Now, maybe my velocity went way above 60, went way below 45, but I still have to pass through this magical 53. Every value between 45 and 60 has to get hit at least once, perhaps more than once, but at least somewhere along the way, that derivative value has to be hit. Just like at least somewhere along the way, I have to pass through any particular y value somewhere on my curve. So differentiability, understanding what the derivative means, when it exists, when it doesn't, and what it gives to us, is an essential part of calculus. It's really a key point in understanding the power of the calculus and what it brings to the table. So once again, this is Mr. Potter. Thank you for watching. Have a great